title is Ensemble Modeling for FMD. And Ensemble, I hope that is matching with a lot of models and not with people, or?
Sorry?
Yeah, ensemble. What kind of ensemble are we going to expect?
An ensemble of models.
Okay.
Yeah. No music, I think. Am I doing this wrong? Oh, there we go. All right, thank you. So I'm going to say a few words about our work on ensemble modeling for FMD. So this has very much been a collaborative work, primarily with Colleen Webb and Lindsay Beck-Johnson at Colorado State University and Michael Tildesley at University of Warwick, who's here today. We've also had the great fortune of working with a range of different modeling teams around the world through various stages of this project, and I'll be coming back later in this presentation to some of the work we've done with some of these models. But we start with the basic. What is ensemble modeling? Before I get into that, I'm just going to say a few words about terminology here. So I will admittedly use the word prediction very loosely defined in this presentation. It's anything we would use, in this case, FMD models to inform. Whereas forecasting would be something we would predict into the future. A projection is something that's expected for a given scenario, where a scenario is a deliberate action, like a control strategy. So under this quite vague definition of prediction, ensemble modeling is simply the combination of multiple predictions, because model predictions would vary. First, if we're talking about stochastic simulation models, the stochasticity in itself produces some uncertainty in the predictions. But also there's underlying modeling assumptions, which in the simplest case would just be parametrizations of a model, but also, and that's what I'm after here, in the most interesting case, we could have structurally different models. So importantly, ensemble modeling is not model selection, because that's concerned with like identifying the best model for a certain situation. It is also not model comparison, which is concerned with identifying the difference between models. Instead, it's the combination of models for predictive purposes. So why would you use this? Well, simply we believe this can improve predictions, make them more reliable. That's certainly the case in other fields of research, and most successfully probably it's been used in weather forecasts, where they found that by combining multiple weather simulators, weather forecasts have improved. It's also been used in a range of other fields of research, but not so much in epidemiology. And we think there could be a point of doing so, because if you're going to use models to inform policy, it seems like a good idea to base these recommendations on a range of different modeling assumptions rather than to rely on just a single set of assumptions. I'm also just going to say that we're probably never going to get to anything as fancy as what they can do in weather forecasts, primarily because they have so much better data than we have. There's weather every day that you can record, and luckily it's at least a new outbreak of FMD every day. Okay, so it seems like a good idea, but then you get to the question how to do it. Because one way or the other, if you're going to combine models, you have to give them weights, like how much is each model going to contribute to the ensemble prediction. This can be done naively, so you just give all the models the same weight, or you can do it by expert opinion. So if you trust some models more than others, you could upweight those models. You could do it based on how they agree with each other. So that could be a way of like downweighting outliers, or you can do it by how they agree with some observed outbreak dynamics. See how do they compare to data somehow. And one of the first things we started with when we started this project was to see, can we adapt some methods used in other fields of research? And we have been focusing on something that's been used in climate science, and it's known as the Bayesian Reliability Ensemble Average method. And it was published in Journal of Climate about a decade ago, when we published a epidemiological equivalent last year. So essentially what it does is that it combines these last two weighting criteria and in its basic form, and we extended it so if you want to, you can also use expert opinion to upweight some models if you want to. So there are at least two situations where you might want to use ensemble modeling. The first is for forecasting. In that case, it's a very clear parallel to the climate implementation where this was first developed for. So what they did there was to run their models for both past and future temperatures, and then you use how well the models reproduce past temperature to inform how much weight each model is going to get when you do an ensemble prediction with all models to do forecasts. So for an epidemiology, what you could do is you would let's see if this which one is the pointer? There we go. So you have time here, and you would simulate your models, and then you reseed them after a while, and then you to do forecasting from like this point. and you would use how well the models capture the state of the outbreak here to inform how much weight each model will get when you projecting into the future. Hang on. So another situation where you might want to use ensemble modeling would be if you want to compare control strategies, right? So one thing you could do there is to run your models for some implemented control where you can compare it. So you run it for an outbreak that we have data for, and you see how well the models do at capturing what happened during that implemented control, and you can inform the weights for the different models when you combine them into an ensemble prediction for the alternative control. I'm not going to go into any much details about the methodology, but what you would do essentially is you would run your models, plug the output from the models into a statistical model together with outbreak data, and then you weighting based on summary statistics like number of infected premises, control culls, etc. And then what you get is the joint probability distribution of the weights of the models together with this predicted quantitative inputs, which again is like the summary statistics of the outbreak, duration, number of infected premises, or vaccine doses, whatever you're interested in predicting. I'm going to skip through this, I think. Okay, so I'm going to say a few words about this case study that we've been working on, focusing on the 2001 outbreak of FMD in the UK. And for this this work, we've used 4 models. So it's the Ospread model, the Warwick model, Interspread Plus, and Exodus. So we can't really go into any details about these models, but they do represent quite a range of different model types, from like more kernel approaches to more detailed simulation models. So what we did was to seed all the models with the outbreak data from 2 weeks after the movement ban was put in place. We then run the models for another 2 weeks with the implemented control, which include the culling of infected premises, dangerous contacts, and contiguous premises. And then reseed the simulations with new information after those another 2 weeks. So if you go back to this conceptual figure, this would be 2 weeks after the movement ban was put in place, and this would be the reseeding event 2 weeks later. Okay. And then we run the models to predicting into the future and do some sort of forecasting. And we look at different time scales, so 2 weeks, 4 weeks, and then the end of the outbreak. And since we're doing these retrospectively, we actually know what eventually happened. So the key question that we're trying to answer here is, does the ensemble actually do better than any of these individual models? And the short answer to that is yes. So in this figure, you have the different time scales here on the x-axis, and this is log of infected premises. So sorry about if that's an unclear scale there, but yeah, these red dashed lines are the observed data, so that's what happened, and these gray arrow bars are the 95% predictive intervals of the individual models, whereas the black one is the ensemble counterpart. And as you can see, it's only actually the ensemble that encapsulates the observed data. So that supports the notion that yes, there is some value of using ensemble modeling. We also ran the models with alternative control strategies, and we focused on 5 control strategies. So the first one again was the implemented control, which had culling of IPs, DCs, and CPs, infected premises, dangerous contacts, and contiguous premises. So then we have one control strategy that's quite moderate, using only IP culling, then one that added DC culling on top of that, and then we had one that added ring culling, and one that instead added ring vaccination. And the key question we try to answer here is, what would the outcome of this outbreak have been under one of these alternative control strategies? And importantly, we're doing this in ensemble context, so we can say, what does these models collectively say about this question? And I'm going to focus on 3 aspects of the outbreak, which is the number of infected premises, number of control culls, and the outbreak duration. I'm also going to say that these results are we're still analyzing this, so they're a bit preliminary, so take them with a grain of salt. But anyway, here they are, beginning with number of infected premises, what this figure is showing. So these arrow bars are the ensemble predictions for each of these control strategies. This red dashed line is the number of infected premises that was recorded for this outbreak. And what does this show? It shows that, okay, had this most moderate strategy been used, they would have had a larger outbreak with more IPs, and only one of the alternative controls, does Ensemble say, would have reduced the number of IPs, and that's the one with ring culling. The other thing you can see in this figure is quite large ranges that's predicted, especially if you look at this last one here. There's a lot of uncertainty from the Ensemble prediction about the ring vaccination strategy, and the reason for that is that there's quite a large discrepancy between the models. They predict very different things here. So some models predict that this would have resulted in more IPs, and other models predict that this would have resulted in fewer IPs. Okay, moving on to the number of control culls. The only strategy where the Ensemble says there would have been at least slightly less control culls would have been for the IP and DC culling strategy. And moving to duration, there's actually no real conclusion from the Ensemble. They all sort of overlap the observed duration of this outbreak. Okay, conclusion. So, at least for this case study here, the Ensemble outperforms any of the individual models. I think this supports the notion that there's some value to using Ensemble modeling. There's quite large discrepancy among the models in terms of the efficiency of the different controls, so that leads to some uncertainty about the efficiency, at least for some of these scenarios. But I still think that it still makes sense to use an ensemble approach here if you're going to communicate this to policymakers, because it's more fair to communicate that, okay, there is a lot of uncertainty for this control strategy, which is because the models disagree. So rather than just like pick one of these models and base your recommendation on that single model, unless you're very, very sure that that's the right one. And finally, just a couple of words about this methodology that we've been using. I think there's some benefits to it. First of all, that it can handle these sort of different model types, like combine them. And I also think it presents uncertainty at different levels in a way that's both easy to interpret and to communicate. So finally, thanks to some people, to some funders and some institutions, and to you for listening. Thank you.
Okay, thank you for this presentation. Are there any questions? Aldo, and any questions?
Yeah, it's something I always try to pass over. That in your modeling you say preemptive culling is so effective, but do you account also for the increased risk of transmission? Because you need a lot of people on premises that are, based on your modeling assumptions, could have been infected or would be infected, and so you're bringing a lot of people that also move to other premises perhaps into without the possibility for good hygiene. So I'm a little bit uncertain if the effect of preemptive culling is a little bit overestimated due to these effects are not taken into account.
Okay. So what we did here is, you mean, are these models including the fact that, so if you send out control culling teams, they would actually transmit the disease? I guess that's risk, and I think some of the models would be able to include that, others wouldn't. So I know, I'm not sure exactly. So what we did here was we let all the modeling teams parameterize and set up their models like they think it would happen, like they make their best version of their model for this problem. And I know some of the models cannot do this, and I think some others can, and I'm not sure exactly how they handled that factor in this case. Yeah. They didn't. Okay.
I mean, I think the thing is that we gave models the freedom to do what they deem to be the best, and it's our role to analyse the ensemble of models together. That's kind of
Okay. Any other questions? Then I have one question. What you see is that your most likely value is a better prediction if we look at the past results, but if you are going to simulate and combine those models, as a decision maker, my uncertainty interval increases. So it's my job. At the last slides you showed.
So you can go back to which one you're talking about. Yes. Is it this one?
Yeah, for example, this one. Mm-hmm. So as a decision maker, I was happy with the old models because it was quite obvious from as a decision maker what kind of strategy to choose. Mm-hmm. And now by combining the models, you make my work harder because you present me a expected result with a huge confidence interval.
Yes, but I think it's more honest to communicate that uncertainty to you as a policymaker than to just pick, for instance, this is what's going to happen. This is one model. Had you picked another one, you would have got completely different answers. Yeah.
I understand that is a more realistic, but it doesn't make the work of policymakers more simple.
Okay, so if I had to choose between two scenarios, where one where all the models agreed, so at least knew there was some positive effect, and one where they were uncertainty but the average effect might be better, I would pick the one where you're at least certain that, so you could base your decision on the uncertainty as well, I think.
Okay, thank you. Any other questions? If not, thank you for your presentation, and we move to the next one.